Hello everyone, this is Bandgar S.S. working as Assistant Professor at Department of Physics, KTHM College, Nasa. Today we have to going to discuss S.Y.B.Sc paper 2nd Instrumentation, that is the semester 3. Today we have to going to discuss chapter Measurement of Pressure, and we have to cover up the various topics like as the introduction of pressure, elastic and electric transducers. Starting with a pressure measurement. So what is the pressure? So the measurement of pressure and vacuum in all industrial processes are most important measure. To avoid many hazards, it is essential to measure and control pressure on liquids or gases or both. It is a quantitative determination of flow rates and mass flow rate of gases or liquids. The pressure and vacuum play very important role in a process control system. So that's why that two terms, pressure and vacuum, are very important in a measurement system. What is the pressure? The definition of pressure is the amount of force is applied per unit surface area on which it acts normally is known as pressure. SI unit of pressure 1 Pascal is equal to 1 Newton per square meter. 1 Pascal is equal to 1 Newton meter square. Or CGS unit 1 bar is equal to 1 dyne per square centimeter. So 1 bar is equal to 1 dyne per centimeter square is equal to 0.1 Pascal or 1 Newton per meter square. So these are the two units of pressure, SI unit and CGS. Different unit of pressure. First one is the atmospheric pressure. It has the unit atmosphere or kilopascal, that is the ATM and kPa. Second one is a manometric units, millimeter, centimeter, inch or foot. Third one is the non-SI metric units, bar, decibar. Third one is the gram force, or it is also known as the ton force per centimeter. Second one is the kilogram force, ton force per meter square. Or next one is the kilogram force or kilopound per centimeter square. Next one is the measurement of vacuum is torr, micrometer or inch. Next one is the customary units, pounds per square inch, PS, or it is also measured meter C, that is the MS term, and feet CFS term. Now next point is the relation of different units of pressure, Pascal, PSI, pounds per square inch, atmosphere, ATM, torr, bar, or technical atmosphere, that is the AT. So when it is the 1 Pascal, that time it is the 1 Newton per meter square, 10 raised to minus 5 bar, or 1.0197 into 10 raised to minus 5 atmosphere. Pounds per inch, 1 pounds per inch, it is the 6.9 10 raised to 3 Newton per meter square or Pascal. Or bar 6.8948 into 10 raised to minus 2. Atmosphere 1.030 into 10 raised to 5 Pascal. Pounds per square inch 14.696 psi. Torr 760 torr 1.01325 bar. Torr is equal to into Pascal 133.32 Pascal, or pounds per inch 1.934 into 10 raised to 2 PS. Bar into Pascal 10 raised to 5 Newton per meter square, 100 kilopascal, or atmosphere 1 ATM. Now technical atmosphere 80 it is the 0.98 into 10 raised to 5 Pascal. Atmosphere 0.9678 atmosphere, or torque 735.56 torque, bar 0.98. Now next concept is the concept of vacuum. Vacuum is generally defined as volume of space that is essentially empty of matter, such that its gaseous pressure is much less than atmospheric pressure. In real practices, no volume of space can ever be perfectly empty. A quality of vacuum refers to how closely it approaches a perfect vacuum. A perfect vacuum, which is simply called vacuum or free space, and use the term partial vacuum to refer the real vacuum. Residual gas pressure in space of interest is a primary indicator of quality and is most commonly measured in units called as a torque. Low pressure indicates high quality. So vacuum, it is nothing but a empty. There is a no volume of space, that is the free space, and when it is the minimum, then you will get the maximum or ideal output of a measure. Now we have to see the different scale of pressure. Now next point is the pressure scale. So what is the requirement of scale? The measurement of pressure. To measure the pressure in a vacuum, high and low vacuum, or sometimes ultra high vacuum, used to vacuum or pressure gauges. It is possible to measure system pressure continuously from 10 millibar down to 10 raised to minus 11 millibar. A pressure gauge is used to measure unknown pressure in absolute unit balances. The unknown pressure against zero pressure or complete vacuum. The unknown pressure can be expressed in gauge scale, absolute scale, or vacuum scale. So these are the three scales to measure the unknown pressure of measurement system. Now this diagram shows the how two different pressure scale are inter. So these are the following pressure scale: absolute pressure, gauge pressure, differential pressure, and atmospheric pressure. So at the zero level, we have to say the absolute pressure of the measurement system. Then we have to go into the upward direction. Then you will get the gauge pressure. You will calculate the differential pressure, and above the vacuum pressure, it is the atmospheric pressure, and above the atmospheric pressure, we have to calculate the atmospheric pressure, or that is the known as the gauge. So starting with the absolute pressure. So absolute pressure is the pressure compared with a zero pressure or empty scale. That is the vacuum. So already we have to know what is the vacuum. It is the free place. It is the empty. So that time we have to say the absolute scale. Or when pressure is zero, that time we have to say the absolute pressure. This scale has absolute zero pressure as the lowest 0 point. The pressure above the reference value of the absolute zero pressure on the gauge scale is nothing but atmospheric pressure is 1. So absolute pressure is equal to gauge pressure plus atmospheric pressure. That is the known as the absolute pressure. Now next one with a gauge pressure. It is the pressure compared with the atmospheric pressure, that is surrounding air pressure. That scale has atmospheric pressure as lowest 0 point. The zero pressure on the gauge scale is nothing but atmospheric pressure of 1 bar or 760 mm of Hg, 14.7 ps. A gauge pressure by convention is always positive. A negative gauge pressure is defined as well. The negative gauge pressure we have to say as a negative, or it is the below of C. Now next type is or scale of pressure is the differential pressure. Differential pressure is simply the measurement of unknown pressure with reference to another unknown pressure. To define the one pressure range, and we have to compare it to the another pressure. That pressure you have to know as the differential pressure. It is the difference between two pressure points. This type of pressure measurement is commonly used to measure the pressure dropped in a fluid system, since differential pressure is a measure of one pressure reference to another. It is not necessary to specify a pressure reference. Now next pressure scale is the atmospheric pressure. It is the pressure exerted by the air surrounding the earth. This pressure varies with altitude, since air nearer the earth is compressed by the air above. Atmospheric pressure is typically about 100 kilopascal at sea. So that is the atmospheric pressure scale of a pressure. Now next concept is the elastic transducer. So what is the elastic transducer? The elastic transducer consists of elastic element which converts the pressure into a mechanical displacement, which is later converted into an electrical form using a secondary transducer. That is known as the elastic transducer. So it converts the pressure into mechanical displacement, mechanical energy, and that mechanical energy converted into a electrical energy. That is the function of a electric transducer. The electric pressure elements are primary sensing elements that are designed to operate under pressure gauge by binding, deforming, or deflecting or moving some device, an amount by which it depends on pressure change. There are three basic types of the elastic pressure sensing. First one is the diaphragm, second one is the bourdon tube, third one is the bellows. The elastic pressure elements are primary sensing elements, so that are operate different pressure range, and these are the two formations like as a deforming and binding in that material, so which measures by a pressure range. So these are the three basic types: diaphragm, bourdon tube, and bellows. So starting with a diaphragm pressure gauge, that is the elastic transducer to measure a pressure, or it is act as a pressure transducer. Diaphragm are used for low pressure measurement in elastic pressure transducer. So the diaphragm are made from elastic metal alloys such as phosphor bronze, brass, beryllium, copper, polythene, teflon, neoprene, animal membranes, etc. A diaphragm is a single disc that is stretched and fastened at its periphery and is exposed to a process. Since process measure is exerted over a relatively large area, this instrument is more sensitive to small changes in pressure. The principle of diaphragm is based on the basic pressure equation, that is, the pressure is equal to force upon applied area. If a small pressure is exerted on large area, the force will be relatively large and it will cause a diaphragm to flex. When we applied a pressure to a large area, the force will be relatively large. It will give the diaphragm as a flex. A mechanical device such as a pin, rod, or bar is usually connected to the diaphragm. so that the amount of flex can be measured in order to determine the amount of pressure exerted. In precision instruments, the diaphragms are generally used in a pair back to back to form an elastic capsule. The diaphragm capsules are frequently used as isolation devices. The natural frequency of a diaphragm can be given by an equation. F is equal to 1 upon 2 pi square root of K upon M equivalent. So M is the equivalent mass of the diaphragm and K is the elastic constant of the diaphragm. The operating frequency of the pressure to be measured must be less than the natural frequency of the diaphragm. So operating frequency of the pressure is measured to be less than the natural frequency of the diaphragm. So diaphragm may be classified in two ways. First one is the metallic and second one is the non-metallic diaphragm. And it contains, or again it is subdivided into two categories. The metallic diaphragm is flat and corrugated diaphragm. Now starting with a first metallic diaphragm, and first subtype of metallic diaphragm is the flat diaphragm. See the diagram: thin plate flat diagram and membrane type flat diagram. See here the thin and here the membrane connected with the diaphragm, and below the diagram shows the displacement. What is the displacement of diaphragm of thin plate and membrane? So when we apply the pressure, so which gives the maximum displacement, thin plate or membrane? So think on that. When pressure is applied to the diaphragm, it deflects the maximum deflection at the center of Y0 can be measured using a displacement transducer. For a thin plate, maximum deflection Y0 is Y0 less than 0.3 T and referring figure. A linear relationship between pressure and deflection exists as Y0 is equal to 3 upon 16 P 1 minus V square upon ET cube into R raised to 4. So where E is a modulus of elasticity of the material, V is the Poisson ratio, T is the thickness of diaphragm, and R is average radius of the diaphragm, and P is the pressure of applied pressure on a thin plate or membrane. So when we allow the pressure or applied the pressure should be less than P max is equal to maximum pressure is equal to 1.5 into T upon R square sigma max. So sigma max self allowable trace of the material. For membrane, the deflection is larger and the relationship between pressure and deflection is nonlinear, which is expressed as for V is equal to 0.3 volt. So P is equal to 3.58 ET upon R raised to 4 Y0 cube. The deflection Y0 for both bending and tension of a flat diaphragm at any deflection is given by an equation PR raised to 4 and ET raised to 4 is equal to 5.86 Y0 upon T plus 3.58 into Y0 upon T bracket cube. This equation is useful in designing diaphragms for any desired characteristics. So this equation is gives to designing of diaphragms for your specific characteristics of a measurement of pressure. Now second type of diaphragm is a corrugated diaphragm. So corrugated diaphragm are also used in pressure measurement, where large deflection are required than flat diaphragms. The relation between pressure and deflection of diaphragm Y0 is highly nonlinear. As the diaphragm deflects, strains of different magnitudes and signs are generated at different locations of the diaphragm. These strains can also be measured by effectively placing 4 strain gauges on the diaphragm. Corrugated diaphragms are of different forms such as sawtooth, trapezoidal and sinusoidal as shown in figure. So these are the corrugated diaphragm. Next elastic transducer is bellows. A bellows a thin walled cylindrical device with deep convolution and are sealed at one end. A pair of matched bellows can be used to measure absolute pressure or differential pressure. The number of convolutions varies from 5 to 20 depending upon the pressure, range, displacement required and the operating temperature. Bellows are usually made of phosphor bronze, beryllium, copper, stainless steel or nickel alloys. Usually one end of the bellows is attached to the transducer case and other end is free to move. When we apply to the pressure to the bellows, so that time when pressure inside the bellows as shown in figure, it will be expand causing the free end to move. The moment of the movable end is measured in order to identify the amount of pressure. Often an external spring is used opposing the movement of the bellows. As result, a linear relationship can be obtained from the equation PA is equal to Kx, where A is area of the bellows, K is the spring constant and X is the displacement of the bellows. Bellows are generally used for low pressure measurement and they are sensitive to vibration. In certain applications, the bellows can be furnished with a restraining spring as shown in figure. The spring opposes axial deflection of a bellows. So that is the working of a bellows elastic transducer. The stiffness is directly proportional to the Young modulus of the material and inversely proportional to the outside diameter and number of convolution of the bellows. The deflection Y of the bellows is given by the equation Y is equal to 2NA PRX square EDQ. N is equal to number of convolution, D is wall thickness, E is equal to Young modulus of the material, R is the average radius of the bellow, A is the effective area of the bellow and P is equal to pressure. Now next concept is the bourdon tube. Bourdon tubes are more sensitive to shock and vibration than diaphragm and therefore used mostly in static measurement. The range of pressure measurement varies from 10⁶ to 10⁸ Pascal. The advantages of bourdon tube are the low cost, simple construction, high sensitivity, high accuracy and high repeatability. So these are the advantages of bourdon tube. So bourdon tubes are fabricated with metal alloys such as cold work brass, phosphor bronze, beryllium copper, stainless steel and nickel alloys. So these are the materials or alloys used for a fabrication of bourdon tubes. So there are three common types are mostly used in a measurement of pressure. First one is the sieve tube bourdon tube, second one is the helical bourdon tube, and third one is the spiral bourdon tube. So starting with a first type, C-type bourdon tube. So see the diagram how to construct the C-type bourdon tube. So we have to use a bourdon tube, then gauge case, lever mechanism, and some pointer techniques which given to the pressure scale. The most common type of bourdon tube is the C-types. This measurement is an oval tube shaped to reassemble the letter C as shown in your figure. One end of the tube is open while the another end is sealed and free to move. The open end is attached to the frame or case of the transducer. As pressure is applied, the tube will start to straighten slightly. The mechanical response is related to the pressure formula. Pressure is equal to force upon area. Since the outside surface of the C tube is longer than inside and the outside side of the C tube has a greater area. The C-type bourdon tube is consequently the force exerted on the outside surface is greater than the force exerted on the inside, causing the tube to the straighten. When it is the straighten, so you will get the pointer changing and you will get the pressure scale. As the tube straightens, seal tip will move. The angular deflection of the free end is taken as measure of the pressure change. The main advantage of this C-type bourdon tube are high sensitivity, good repeatability. The scale on the dials of some pressure gauge include readings below zero. These gauges are referred to as compound gauges and are often used to indicate vacuum. Now, second type of bourdon tube is helical bourdon tube. Pressure given to that helical type tube and there is deflection, that how much pressure we have to apply, so that much deflection we have to given as a pressure. A helical bourdon tube, an oval tube that is wound into a helix as shown in figure. Its shapes reassembles a coil. The helical bourdon tube operates on the same principle as the C tube, except that the tube is coiled into a multi-ton helix within 5 to 10 tons. One end of the tube is closed and is free to move while the other end is open and firmly attached to the transducer case or frame. The pressure to be measured is applied through the open end, causing the tube to try to uncoil. The tip of the tube moves in response to the movement of the coil caused by the pressure. The advantages of the helical tube is that it produces more tip movement than C. Now, C-type and helical bourdon tubes has the angular deflection. So that angular deflection can be expressed as theta upon theta 0 is equal to 1.16 PR square upon TEB. So where theta is angle of rotation of the tube, theta 0 is equal to angle of tube for C tube or total angle of helix for helix tube. T is the pressure in Pascal, T is the thickness of walls of tube, E is equal to modulus of elasticity, T is thickness of wall tube, and B is minor axis of tube, and R is equal to radius of curvature. So that is the angular deflection mathematical expression of a C-type and helical bourdon tube. Now Next, third type of bourdon tube is the spiral bourdon tube. Connection like that given to the inlet pressure, and here magnifying mechanism to a pane. A spiral tube. In spiral tube transducer, the oval tube is wound in a spiral form as shown in figure. The major advantage of this type of bourdon tube is that the tip produces more motion than both C and helical tubes. In this tube, the radius of curvature increases with each turn. The tip of travel due to its multi-turn configuration increases depending upon the number of coils. So, the number of coils depending upon the tip travel of the multi-turn configuration increases. The deflection of the bourdon tube varies with the ratio of its major to minor cross-sectional axis, length of tube, radius of curvature, difference between the internal and external pressure, and angle of twist. It also varies inversely with modulus of elasticity of the material of tube and the wall thickness of tube. Now, the various types of pressure transducer. Now, next type is the electrical type pressure transducer. So, most of the electric pressure transducer are used for a pressure measurement application. So, we have to know the very popular type transducer. First one is the LVDT, linear variable differential transformer. Second one is the strain gauges. It has the two types, bonded strain gauge and unbounded strain. So these are the electrical pressure transducers. Now starting with a LVDT, linear variable differential transformer. That is the LVDT. See the diagram. This is the LVDT connection, and there we have to use the as a bourdon tube to apply a pressure. So when we apply pressure to the bourdon tube, so that time bourdon tube is straightened and due to the deflection of core, and when we deflection of core is deflect, so you will get the output voltage across a LVDT. So AC voltage is connected to the primary winding of the transformer. Secondary winding consists of two windings that are connected so that there are outputs at opposite polarity. A movable core is attached to a mechanical pressure sensing device such as diaphragm, bellows or bourdon tubes. So here we have to use a bourdon tube. If process pressure changes, the mechanical sensing elements will move, causing the movable core to move. If an instrument is connected to the voltage induced output of the transformer, it will indicate a pressure. Now consider a bourdon tube acting as a primary detector which senses pressure and converts it into a displacement of free end of the displacement of the free end moves the core of the LVDT, which in turn proportional to the movement of the core and in turn proportional to the displacement at free end of bourdon. So there are two stages of transconduction. First, pressure is converted into displacement and by bourdon tube, and the LVDT, the displacement is converted into a analog output voltage. Now next one is the strain gauges. We have to see in the second electrical type pressure transducer, and these has the two types. First one is the bonded and second one is the unbonded. Now starting with bonded strain gauge, the basic principle of strain gauge is that the cross-sectional area is changed, then wire resistance will also change. Same you will get the in terms of resistance and you will get the into a output voltage. The wire resistance can be manually adjusted by stretching and straining the wire. See the diagram. you have to use the strain gauge wires, and we have to stretching and straining the wires. You will get the change of resistance of wire and you will get the desired output. And we applying the stretching and straining pressure, it will be a measure. The resulting changes in resistance allow strain gauges to indicate changes in a process pressure. Unbounded strain gauge consisting of stationary member and the movable armature, which have insulated pins that supports a series of small wires. The moving armature of an unbounded strain gauge is connected to a mechanical sensing element such as diaphragm. When pressure changes, the mechanical pressure element will move the movable armature to change the tension on the wires, will change the resistance. Bonded strain gauge. In bonded strain gauge, small wires are pieces of foils or bonded piece of insulating material with adhesive material. See the diagram, first one. So there is the small wires or pieces of foils are bonded as piece of insulating material, that is the adhesive. When it is used to measure a pressure by using a bonded gauge, is fastened to move some movable part of mechanical pressure sensing element. The deflection of the diaphragm alters the gauge resistance and unbalances as a associated bridge. So we have to use a 4 arms of a stone bridge which improve the sensitivity while remaining the temperature compensation in a bonded strain gauge. Now next concept is the deadweight tester method, that is the pressure calibration purpose. So see the diagram, we have to use a 2 cylindrical tubes and we have to use weights and plungers and pressure sensors. So deadweight tester is widely used device for pressure calibration which provides the desired starting and ending pressure profile. The deadweight tester consists of 2 accurately machined cylinders inserted into 2 closed and known cross-sectional areas coupled together to a reservoir, as shown in one of the 2 cylinders are fitted with close-fitting frictionless movable pistons with a top plate. On this platform, accurately known weights in the form of discs can be added. The pressure transducer to be tested is connected to another cylinder. The screwed plunger is provided to the reservoir to apply pressure to the fluid. The fluid pressure is gradually increased by screwed plunger until the force is large enough to just lift the precision piston weight combination. When the piston is floating freely, the pistons with weights is in equilibrium with a pressure developed in the cylinder, that is the pressure of the fluid. This pressure is equivalent force of the piston weight combination and a cross-sectional area of the cylinder. So P is equal to F upon A. The same pressure is applied on the transducer connected to the another cylinder by changing the weights appropriately. The sensor can be calibrated to a high order of accuracy. Advantage of this method is that it can be used in high precision measurement with an accuracy as high as 0.01%. Measured directly in terms of weight, it is a standard device in the laboratory to calibrate the pressure gauges. Thank you.